Okay, well, perhaps you didn't know, but now you do, that technology has some glitches sometimes. So we are going to start again proving this theorem and the corollaries because the first take of this part didn't work. So here we go. I'm not exactly sure where it cut off, but we're going to start here at the part 1, number 6. I am going to draw OA because 2 points determine a line. And so now I have point A, OA. OP equals OA. Why is that true? Well, OP and OA are both radii in circle O, and so all radii of a circle are equal, so those two radii are equal to each other. Number 8, angle PAO equals angle P. Why is that true? That is true because in a triangle, if you have two sides that are equal, the angles opposite those sides are also equal. So we have an isosceles triangle with two angles that are also equal, angle P and angle PAO. Number 9, angle P plus angle PAO equals angle AOB. So when I add those two angles together, they equal this angle out here. Why is that the case? What is the relationship of angle AOB to the triangle AOP? It is an exterior angle. And what do we know about an exterior angle of a triangle? An exterior angle of a triangle is equal to the sum of the two remote interior angles. So this angle up here at A and this angle at P are the remote interior angles, so when we add them together, they equal angle AOB. All right, angle P plus angle P plus angle P then equals angle AOB. Why is that true? That is a matter of substitution because angle P is the same as angle PAO that we added before. So 2 times angle P equals angle AOB. That's part of the same step of substitution. We just combine there. Now if I just divide both sides by 2, I have angle P equals 1/2 of angle AOB, or angle AOB divided by 2. And that is simply division. And then number 17, the measure of arc AB, equals angle AOB. Why is that? Well, that is back from lesson 3, that the measure of an arc equals the central angle of a circle is the degree measure of that arc. And therefore, since angle let me write that down, angle AOB equals the measure of arc AB, then number 13, angle P equals 1/2 the measure of arc AB. And why is that true? And that is simply a matter of substitution there. So just to make that a little more clear, let me say that if I take the measure of angle AOB and divide that by 2, that's the same as the measure of arc AB divided by 2. And this and this are the same, 1/2 of the measure of angle AOB, 1/2 of the measure of arc AB over 2. And so then I'm taking this and this in my substitution to get that. So they kind of added a step there that they didn't spell out very carefully. All right, that's the first part of that proof. The second part of that proof, if we're going to look at a case where the center of the circle is inside of the intercepted arc. So there's A. Over here I still got point P. And I got A going this way and PA going this way and PB going this way. And I want to still prove that the measure of angle P is half the measure of the intercepted arc. That's what I'm trying to prove here, just with a different case. So number 14, the first thing I'm going to do is draw PO, and I'm going to extend it through till it hits over here at point C. And why can I do that? Because 2 points determine a line. PO determines a single line, and I can just carry it on as far as I need to or want to. Number 15, angle APB, that's this big angle here, equals angle 1 plus angle 2. Angle 1 is what we're going to call that upper angle, and angle 2 is what we're going to call that lower angle. So angle APB equals angle 1 plus angle 2. We might call that common sense, or we might call it the betweenness of Ray's theorem. All right, that's the actual answer. Okay, because angle 1 equals half of arc AC, that's what we proved in our first example, that when one of the sides of the angles goes through the center of the circle, that works. So angle A equals half of arc AC, angle P equals half of arc CB. Therefore, we can combine those together and get that that equals half of the measure of arc ACE, or AC plus the measure of arc CB. And why is that? That is simply substitution. So half the measure of this arc plus half the measure of this arc. Number 17, the measure of arc AC plus the measure of arc CB equals the measure of arc AB. This smaller arc plus this smaller arc equals this arc, the measure of that arc altogether. That's what the arc addition postulate says. And number 18, angle APB equals half the measure of arc AB then because of substitution. There is one more way that can be proven, another case that would be proven. We're not going to do that. The book doesn't pull that out here, but we could look at the case of an inscribed angle that didn't contain the center of the circle at all. Both rays were on the same side of the circle. That would be a third case. We're not going to worry about proving that case though today. All right, corollary number 1. We want to prove that inscribed angles that intercept the same arc are equal. And so we talked about that a little bit before when we were introducing that corollary, but let's look at this briefly. Number 20, because angle A and angle B are inscribed angles, the measure of angle A, or the angle A equals half the measure of CD, and the measure, or angle B equals half the measure of CD also. That's just what we learned, that the measure of an inscribed angle equals half the measure of the intercepted arc. Therefore, with substitution, angle A equals angle B. All right, corollary number 2. An angle inscribed in a semicircle is a right angle. And again, we went through that proof real briefly when we introduced this lesson, or that corollary. Number 22, let me just run through these answers for you though. Number 22, that is because the measure of a semicircle is 180 degrees. Number 23, angle A equals half the measure of arc ADC because an inscribed angle is equal in measure to half of its intercepted arc. Number 24, then the angle B equals half of 180 degrees, which is 90 degrees. That's substitution. Therefore, angle B is a right angle because 90-degree angles are right angles. All right, then lastly, we're going to do this inscribed triangle problem. This is a nice problem. It's real important to me that you understand this problem well. So don't just watch this, but tune your brain out. I want you to watch this and have your brain tuned in clearly and follow along well. So we're going to draw this triangle. I actually strongly encourage you to draw this triangle at home. I know that you can just look at what's in your book, but I think that it might help your brain follow it and process it a little better if you draw it yourself. So I would suggest that you draw it yourself. So we have triangle ABC, and from point O, then we have radii coming down. We are given this arc is 100 degrees, this arc is 120 degrees, and arc BC is 140 degrees. And then we're also given some things that we need to solve for. We've got X up here, we have Y right here, and down here we have Z. All right, X, Y, and Z. So, with respect to the circle, what are the three angles whose vertex are at O called? So there are three angles whose vertex are at O, 1, 2, and 3. What kinds of angles are those? Those are central angles because their vertex is on the center of the circle. Number 28. What are the three angles of triangle ABC called? So this angle here, and this angle here, and this angle here. With respect to the triangle, what are they called? Well, those are inscribed angles. Their vertex is on the circle, and their sides intercept the circle into other places. All right, number 29. Find the measure of angle AOB, of angle BOC, and of triangles, or of angle COA. So AOB, how big is that angle there? Well, that angle is a central angle. It intercepts arc AB, and arc AB is 100 degrees. Therefore, this angle here is also 100 degrees. Similarly, angle BOC here intercepts arc BC, which is 140 degrees. That makes this a 140 degree angle. And likewise, arc CA is 120 degrees. Its corresponding central angle is COA. So that also is, that's the same measure then as that arc, 120 degrees. All right, number 30, use your answers to find X, Y, and Z. So I have a bunch of isosceles triangles here. They're not congruent to each other, but they are isosceles. So triangle AOB, I have X angle over there. I have another X over here. Those two angles are equal to each other. So 100 degrees plus X is 180 degrees. That makes each of these angles 40 degrees. So X is 40 degrees. Y, I similarly have another Y angle over here, and that angle plus this angle plus 140 degrees equals 180 degrees. So 2Y is 40 degrees, so each Y is 20 degrees. And lastly, I've got a Z angle down there, and this angle here is also Z. Each of these plus 120 equals 180, so each of those angles at Z then is 30 degrees. They combine to be 60. All right, excellent. Use X, Y, and Z to find the measures of angle ABC, ABC, CB, CAB. Okay, those big angles. So, angle A then, angle A equals X plus Z, 40 plus 70, 40 plus 30.